going to now work problems that were found on exam number 2. This will be pretty much the same as the test you actually took. Um, so here's the first question, or one of the questions, the first one I'm going to work. There's this fictitious element, the strangest element on Earth, named B-Lancium, which you probably would agree with that by this time in the semester. But it was analyzed, and we have to determine the mass, the exact mass of a particular isotope of B-Lancium, Bl-113. And we're given some information in the problem about the other two isotopes, Bl-110 and Bl-112, and we're given the weighted average atomic mass of the elements. So when you put all the isotopes together with their abundances, it comes out to be that as a mass. And you're also given in this problem a figure to look at that gives you the fractional abundance for each individual mass. So using these abundances that are here, we were going to figure out what the atomic mass is for that Bl-113. So it's very simple. All you have to do is understand that when you multiply all of these individual masses by their abundance and add them all together, they have to come out to equal this number. So you really end up, you're looking at the 110 B, or little l, Bl times its abundance, right, added to the 112 Bl times its abundance, plus the 113 Bl times its abundance. That's a good A. There we go. Is going to all add up to 110.691. Like that. So we're given everything that we need with the figure and the problems in the written words here. So for Bl-110, it's actually 110.120 AMU multiplied by its abundance, which was found on the graph. So you go to the figure, and it's 0.75410. So you just multiply, you're going to multiply that, 75410. And then you're going to have Bl-112, which is really 11.920. So 11.920 times the abundance from the graph, 0.1, this is it, 0.12330. We don't know the exact mass for the 113, but we do know from the graph there is somewhere around in here where it would probably be found. There's an abundance of 0.12260. And all that has to add up to 110.691 atomic mass units. So now we just need to multiply these two, so because we can go ahead and get these added together if we do that. So I'll just real quick just pull my calculator. So there's 110.120 times 0.75410, and then you have that number, and then that will be reported to 5 sig figs. 1, 2, 3, 4, 5. Or I could just, wait, and since I see right away that this is going to be 5 sig figs also, and it's not going to change anything too much, but I'm just going to add to that answer, and I'll just put that in parentheses, and it's 111, excuse me. I have a little typo right here, as you can probably see. You probably noticed that already. But anyway, so 111.920 times its abundance of 0.12330, and I get that number right there. So this part simplifies to 5 sig figs at 96.841 AMU plus the 113 BL. I don't know, but I do know the abundance from the graph, and it has to add up to equal that. Now, I'm very close. I just go ahead and I need to move this over, so I'm going to subtract it from both sides. So on my calculator, I have the 110.691 minus the 96.841, and you get 13.85, but you need to keep that third decimal place, so it's 0.850, so 13.850 over here, and that's equal to the 113 BL times the abundance, 0.12260. Now I just have to divide both sides by the 0.12260, and I get 5 sig figs. So the 113 Belancium will be 112.97 AMU. 112.97. So that's the actual atomic mass for Belancium 113. So if you just take your time and look at what all you have, you should be able to solve a problem like that using the information given in the wording combined with the information provided in a figure such as this.